Welcome back to our custom code example for linear regression with Python and Spark. What we're going to do is walk through a more realistic example of linear regression. We saw the basic workflow using the documentation example, but let's examine some e-commerce customer data for a company's website and a mobile app. The main idea is using various features, we're going to try to predict a customer's total amount expenditure, which is just a continuous money value. And we'll also discuss how to convert realistic data into a format accepted by Spark's MLlib. The documentation example already had it formatted that way. Realistically, you're not going to have it in that format, so we'll show you how to convert it into the Spark MLlib format. The relevant notebook for this lecture is called Linear Regression Code Along. Let's get started. I'm going to hop over to my browser with a new notebook with access to the data. All right, let's get started. First we need to do is say from PySpark.sql import a Spark session, and we'll actually create that Spark session now. Hopefully by now you're kind of used to doing this. We just create an example and then get or create. Shift enter, our Spark's ready to go. And what we're going to do is right off the top say from pyspark.ml.regression import linear regression. We won't use this right away, but we will use it in just a little bit. Now let's get our data. So our data is going to be Spark read.csv, and I'm going to be using the ecommerce_customers.csv file that's available to you in the notes under the linear regression folder. And I will also say infer schema is equal to true, and I'm also going to say that the header is true. And then once we've done that, it may take a little bit of time to read depending on how fast your computer is. What I want to do is just print the schema so we can explore the data just a little bit. And I can see it has an email, which is a string, an address, which is also a string, some sort of avatar, we'll see what that is in a second. Average session length, that's a number. Time on app, also a number. Time on website, also a number. Length of the memberships, how much time has this customer been a member, and then their yearly amount spent on the service or the site. And that's the kind of variable that we're going to be trying to predict. Now for your own custom examples, you're going to have to clarify what you need to predict. Right now I'm just telling you that this is the actual value we're trying to predict. So let's show what the data actually looks like. If I just hit show, it's probably going to be too zoomed in for us to kind of get a good idea. So it's a little messy. So instead what I'm going to do is just show you head of 1 so we can see what the value actually looks like. And now let's actually say 4. Well, we'll say 0. So that's the actual row. And I'll say for item in this print item. All right, so here we can see the actual value. So this is the email value. We can see here that there's actually an address as well. So Frank Tunnel, whatever. Then there's the avatar, and the avatar is actually just a color. So if I take a look at another example, such as here, head 2, whoops, it's actually not what I wanted. Head 2, 1. Here we can see dark green. So they're just various colors. And then we have actual numeric values for these things right here. The average session length, time spent on the app, time spent on the website, the length of the membership, so that's in years, and then yearly amount spent. So this is all fake data. I generated this myself, so don't worry, these aren't real emails or anything. Well, hopefully they aren't real. Okay, so moving along, we're going to set up the data frame for machine learning. And this is one of the most important features of using and understanding how to use MLlib, especially with Python and Spark. So this is something you're really going to want to get down. The first thing you have to do is to import the vector assembler and vectors. So we'll say from pyspark.ml.linalg import vectors. Now we don't actually use this directly, but often in the documentation you see it imported anyways. So I always like to do it just in case it's a requirement. So we'll say from pyspark.ml.feature, and this is where we're actually going to be using something. We're going to say vector assembler. All right. So this is what we need to do. We need to convert all the numerical columns that we're going to be using. We won't work with the actual categorical columns. We won't work with the address or the email or this avatar. We'll see how to work with those later on in future examples. Right now I just care about this numerical data. So I want to grab this numerical data as the features, and I want to grab this as the label to predict. So let's continue on and show you how to use vector assembler. So again, if I say data columns and show the column names that I want, the only things I'm interested in are the average session length, the time on the app, time on the website, the length of the membership, and this yearly amount spent. That's going to be my label column. So let's continue on by creating an assembler object. So we'll call it assembler. You can really call it whatever you want, but it's going to be a vector assembler. and it takes in the following arguments. Whoops. It takes in input calls, and input calls is a list of strings of the actual columns you want to take in. So in this case, this is going to be all our feature columns. So we say input columns, and we can just copy and paste that here. So we have average session length, time on app, time on website, length of membership. And if you want, you can format this so it looks a little nicer than what I have here. So let's kind of put this all on one line. I'm zoomed in, which is why it looks a little strange here. But there we go. And now after this, what we're going to do is say, okay, so input calls, that's one of the arguments. The other argument we're going to be doing is, whoops, is the actual output column. So output call is equal to features, or whatever you want to call. But basically the idea behind vector assembler is, I can zoom out just a little bit so we can see the whole thing, is you have a list of input columns, and those are the input columns you want to be the features, and then you have an output column that's just a single feature. So it's going to grab all these columns and turn them into a single vector. So we have our assembler there, which is basically just saying, okay, this is what to expect. The next thing we want to do is actually transform the data. So I'll create an object called output, and this will be that assembler object that I just made, and I will call the transform method, and I pass in my original data. And I'm passing in all my data. I haven't done the train test split yet, and that's important. So I'm passing in all my data, and if I take a look at what the print schema of my output, I have everything that I used to have, and I have this new features column. To get a better idea of what this actual features row looks like, let's select it. So I'm going to say output head 1, and I can see here that this features object is a dense vector consisting of, we zoom in just a little bit here, of the values that I inputted. So we can see here we have essentially what looks like a vector or array, and it's a combination of all these numerical values that I wanted. Perfect. That's exactly what we want, and that's the kind of format that Spark is going to be expecting for linear regression or really any machine learning algorithm. So now the next step of what I want to do is select my final data. You don't actually have to do this, but I recommend it because it kind of tightens everything. So we'll say final data is output, select, and all I care about is that features column that contains all the features I want, and then the yearly amount spent column. All right, so I have my final data, and if I show my final data, I can see here's that features column, and then what is essentially my labels column, yearly amount spent. So now let's split this up into a train test split. So I'll say training data, comma, test data, so using kind of tuple unpacking here. And I'll say my final data, call random split on it. And by convention, a 70-30 split is really common. 60-40 is also really common, as well as 80-20, depending on what kind of data you have, how easy it is to train on that data. There's no real right answer on what you should do a split, but if you just want to kind of choose a default split, 70-30 is a pretty good choice. So that's what we're going to do. We'll do train test. And now what we want to do is see and confirm that everything actually looks good. So let's kind of show the training data. All right, so we have 357 in our training data, and now what I'm going to do is copy and paste this for the test data. All right, and we have 143 in our test data. Good. So our train test split worked perfectly. Now let's create our linear regression model. So I'm going to create an object called LR, and this is going to be my linear regression model. And remember, if you look at your linear regression model, we had to define the features column, the label column, and the prediction column. The defaults are fine to use as long as you match up with the defaults. Now, our label column isn't called label. Instead, it's called yearly amount spent. So let's actually adjust this by saying the label column is going to be called yearly amount spent. If we come back up here to when we were looking at our features column, that is the same name as the default value, so that's totally okay. We'll leave that the same. So we have yearly amount spent as our label column. And then what I'm going to do is create a linear regression model, and I'm just going to, let me kind of zoom in here. All I'm going to do is say LR fit, and I'm going to fit to my training data. So we'll fit to our training data, let that run. Again, depending on what kind of computer you have, it may take a little bit of time. And now it's time to see how well our model actually performed. So in order to do that, we need to evaluate it against some test data. So I will create test results is equal to LR model evaluated or evaluate on the test data. So now I have these test results, and if I take a look at the test results and their residuals, I can show these residuals. And the residuals is just the difference between the predicted value and the actual label from the test data. So let's scroll down here, continue on, and get some of those regression evaluation metrics that we discussed earlier. The way I'm going to do that is just by calling test results, and then what I can do is call the root mean squared error. So that's my root mean squared error. And then we can also call from test results, you can call r squared, and that's 0.98. So this kind of indicates that we're explaining a lot of the variance. This is a very good model just from the root mean squared error and the residuals, because if you look at the actual original data, so if we look at final data, describe.show, describe.show. As we begin to finish up this lecture, there's two more things I want to do. One is to actually go over these results, this root mean squared error, r squared, compared to that final data. And the second thing I want to do is just quickly review how you could deploy this model on some totally unlabeled data. So not just test data, but only data that you have features for. So let's quickly review what's going on here. This number, the root mean squared error, remember that's the difference between your test value, that true value, versus the predicted value. So you take that difference, you square it, which in turn punishes larger errors. And to turn it back into the same units, in this case, yearly amount spent, or let's say dollars spent, we take the square root of that whole thing. So I can see that my root mean squared error is around $10.50. By itself, that number is pretty meaningless. What you have to do is compare it to the actual column value, that actual label that you're trying to predict. In this case, it's yearly amount spent, and the average yearly amount spent is $500, with a standard deviation of $80. Minimum was 256, maximum was 765. So I can see here, in comparison, being off on that root mean squared error by $10.50 versus the actual average being $500 and the standard deviation being $80 is actually pretty darn good. To confirm that I have a good fitting model, I can also check out the r squared value, where the r squared value is saying my model explains 98% of the variance in the data. That's also very good. Now, having such a good root mean squared error and also having such a good r squared value should kind of ping something in the back of your mind saying, okay, I should double check this data, double check the way I fitted my model, make sure you didn't accidentally fit your model on the training data, and then also evaluate your model in the training data. That's kind of a common mistake. However, you can rest assured here, because I artificially created this data, it was designed to have a very good fit by a linear regression model. You can expect more advanced or more complex models to have better fits, but for something as simple as linear regression, you should definitely double check if you get results this good on a real data set. Okay, so that was reviewing the results. Let me just quickly review how you would then essentially deploy this model on some data that you only had the features for. So let's say we have some customers where we only have their features, but we don't know how much they are actually going to spend in a year. To mimic that, what I'm going to do is say I have some unlabeled data, and that's going to be equal to my test data. However, I'm only going to select the features column from it. So if I look at my unlabeled data, I can see it only has features. It doesn't actually have the yearly amount spent. So we can treat this as some new incoming data that I want to deploy my model on. So let's scroll down here, and I'm going to say, grab my model, and I will transform that unlabeled data, and then set that equal to predictions. And what predictions is, as a reminder, it is a data frame where it shows the incoming features and the predicted yearly amount spent. So for this first customer with this specific feature, or this vector of features, I predict in a year they will spend $330. For the second customer, I predict they'll spend this much, etc. And if I check this against the test data, which is exactly what we did up here when we said evaluate, if we scroll up here, when we said evaluate, what this ends up doing is it grabs that residual information, that root mean squared error information, etc., all from comparing that prediction versus what it knew to be the true value. All right, I hope you enjoyed that discussion, and I hope it gave you a good idea of how you can apply these techniques to a more realistic looking data set. Coming up next is going to be a consulting project. So we'll start off by giving you a little bit of background on the project itself, what the data, and what the expected output is. Thanks, and I'll see you at the next lecture.